One of the leading contributors to gamma-ray burst theory is the astrophysicist Stan Woosley. His research helped develop models in which certain gamma-ray bursts occur when extremely massive stars collapse into black holes. In this scenario, the collapsing star forms a rapidly rotating disk of matter around the newly formed black hole. Jets of high-energy particles are launched outward along the star's rotational axis at speeds approaching that of light. When those jets break through the outer layers of the star and blast into space, they produce intense beams of gamma radiation detectable across enormous distances. Because the jets are highly focused, gamma-ray bursts are visible only when one of the beams happens to point toward Earth. For a few seconds, the burst becomes one of the brightest events in the observable universe. Then it fades. Another remarkable source of cosmic violence arises when neutron stars collide. Neutron stars are already extreme objects. Formed from the collapsed cores of massive stars, they contain more mass than the Sun compressed into a sphere roughly the size of a city. Their gravitational fields are immense. When two neutron stars orbit each other in a binary system, they gradually spiral inward as they lose energy through the emission of gravitational waves. These waves are subtle ripples in space-time itself, predicted by Albert Einstein's theory of general relativity. As the stars draw closer together, their orbital motion accelerates. Eventually they collide in a violent merger that produces a burst of gravitational waves and electromagnetic radiation. The collision can also forge heavy elements such as gold and platinum through a process known as rapid neutron capture. For many years, gravitational waves remained purely theoretical. But in the early 21st century, scientists built instruments capable of detecting these incredibly subtle distortions of space-time. One of the most important facilities for this work is the Laser Interferometer Gravitational Wave Observatory, widely known by its acronym. The Laser Interferometer Gravitational Wave Observatory consists of large detectors located in the United States that measure tiny changes in distance caused by passing gravitational waves. The observatory was developed through decades of research led by scientists including Rainer Weiss, Kip Thorne, and Ronald Drever. In the year 2015, the observatory made history. It detected the first confirmed gravitational waves produced by the merger of two black holes more than 1 billion light-years away. The signal lasted only a fraction of a second, yet it revealed an event of enormous energy occurring deep within the cosmos. A few years later, another detection captured the gravitational waves produced by merging neutron stars. For the first time, astronomers were able to observe both gravitational waves and electromagnetic radiation from the same cosmic event. Telescopes across the world quickly turned toward the region of the sky where the merger occurred. They watched as the collision produced a glowing cloud of expanding debris. Even these astonishing events, however, remain separated by staggering distances. Between one violent event and the next lies an ocean of empty space. The universe contains enormous energy, but it is distributed across volumes so vast that most of it never interacts. Another example of extreme astrophysical phenomena involves objects known as magnetars. Magnetars are a rare type of neutron star possessing magnetic fields of extraordinary strength. These fields are so powerful that they can distort the very structure of atoms near the star's surface. Theoretical work by astrophysicists Robert Duncan and Christopher Thompson helped explain how such intense magnetic fields might form. According to their models, certain rapidly rotating neutron stars can amplify their magnetic fields through a process similar to a dynamo, creating fields trillions of times stronger than Earth's magnetic field. When the magnetic field lines within a magnetar shift or fracture, they can release sudden bursts of high-energy radiation. These events are sometimes called starquakes. For a brief moment, a magnetar flare can release as much energy as the Sun emits in hundreds of thousands of years. Yet even these spectacular outbursts are swallowed by cosmic distance. A magnetar flare occurring in a distant galaxy might travel millions of years before its radiation reaches Earth. By the time the signal arrives, the event itself is long over. What remains is a faint whisper of a once violent moment. This pattern repeats throughout the cosmos. Stars explode, neutron stars collide, magnetars flare, black holes consume matter and launch jets of radiation across intergalactic space. Each event represents an extraordinary release of energy. But because the universe is so vast, these events occur far apart from one another. They rarely overlap, rarely interact, and rarely disturb the calm appearance of the cosmic landscape. Seen from afar, the universe appears tranquil. Not because nothing happens, but because everything happens so far away. Violence exists throughout the cosmos, yet it is diluted across unimaginable distances. The enormous spaces between galaxies and stars act as buffers, spreading energy so thinly that most of the universe remains quiet and dark. This immense quietness raises another question. If powerful astrophysical events occur across the universe, and if light and other signals travel vast distances through space, then perhaps other forms of signals could also exist. Signals created not by stars or black holes, but by intelligent beings. And yet, despite decades of listening, the cosmos remains strangely silent on that front as well. For much of human history, the night sky appeared quiet, simply because the universe is vast. But during the 20th century, a new question began to emerge. If the universe contains hundreds of billions of galaxies, and each galaxy contains hundreds of billions of stars, then somewhere among those countless worlds there might be other civilizations capable of building technology. Civilizations capable of transmitting signals. Civilizations capable of communicating across space. Yet when astronomers listen carefully to the sky, they hear nothing that clearly comes from intelligent life. This puzzle is often summarized in a simple question, first asked by the physicist Enrico Fermi. Where is everybody? Fermi reportedly raised this question during a casual lunchtime conversation in the early 1950s at Los Alamos National Laboratory. The discussion began with speculation about extraterrestrial travel and the possibility of advanced civilization spreading across the galaxy. But Fermi pointed out something curious. If intelligent civilizations were common in the Milky Way, then some of them might have had millions of years to expand, explore, or communicate. Even at modest speeds, a civilization capable of interstellar travel could theoretically spread throughout the galaxy over cosmic timescales. And yet, the sky remains quiet. No obvious spacecraft, no unmistakable signals, no clear signs of vast technological structures surrounding distant stars. The apparent contradiction between the large number of potentially habitable worlds and the lack of detected civilizations became known as the Fermi question, or sometimes the Fermi Paradox. The paradox arises from a simple comparison. The universe seems enormous and full of stars, but evidence of extraterrestrial intelligence appears absent. To explore this problem more carefully, astronomers and scientists developed ways to think about the probability of intelligent life emerging elsewhere. One of the most well-known approaches is the Drake equation. The Drake equation was introduced in 1961 by the American astronomer Frank Drake during a scientific meeting focused on the search for extraterrestrial intelligence. Rather than attempting to produce a single precise number, the equation provides a framework for thinking about the many factors that might influence the existence of technological civilizations. It considers several ingredients: the rate at which stars form in a galaxy, the fraction of those stars that possess planetary systems, the number of planets that might support life, the fraction of those planets where life actually arises, the fraction of life-bearing worlds where intelligent species evolve, the fraction of those species that develop technology capable of sending detectable signals, and finally, the length of time those civilizations continue transmitting such signals. When these factors are multiplied together, the result estimates how many technological civilizations might exist within a galaxy at any given time. The Drake equation does not provide a definitive answer, because many of its variables remain uncertain. but it highlights an important idea. The silence of the cosmos may not necessarily mean that intelligent life is rare. Instead, it may reflect the difficulty of detecting civilizations across the immense distances of space. Still, the question remains: if intelligent life has emerged elsewhere, why have no signals clearly appeared? Several explanations have been proposed. One possibility involves a concept known as the Great Filter. The Great Filter idea was developed by the economist and philosopher Robin Hanson. It suggests that somewhere along the long chain of steps required for intelligent life to develop, there may be an extremely difficult barrier. This barrier might occur early in the process, perhaps making the origin of life itself incredibly rare. Alternatively, the filter might occur later, preventing civilizations from surviving long enough to spread across the galaxy. If such a filter exists, it could explain why the universe appears quiet. Perhaps very few civilizations ever reach the stage where they can communicate across interstellar distances. Another intriguing idea is known as the zoo hypothesis. This concept was proposed by the scientist John Ball, who suggested that advanced civilizations might deliberately avoid contacting developing worlds such as Earth. According to this idea, Earth could be treated somewhat like a protected wildlife preserve, a kind of cosmic zoo. In this scenario, advanced civilizations might observe emerging societies without interfering with their development. They might even hide their presence to avoid disrupting the natural evolution of young civilizations. While this idea remains speculative, it highlights how little is truly known about the behavior of hypothetical extraterrestrial cultures. Even if other civilizations exist, their priorities, technologies, and communication methods might differ greatly from human expectations. Meanwhile, scientists on Earth have continued searching for signals that could indicate intelligent activity. One of the most prominent organizations involved in this effort is the CT Institute, whose name stands for the Search for Extraterrestrial Intelligence. Researchers associated with the CT Institute use radio telescopes to scan the sky for unusual patterns in radio waves. These observations look for signals that might stand out from natural cosmic emissions. For example, a narrow-frequency transmission that repeats in a structured pattern could potentially indicate an artificial source. So far, despite decades of observation, no confirmed technological signal has been detected. The sky remains quiet. This does not necessarily mean that signals are absent. It may simply reflect the enormous challenge of searching across the vast electromagnetic spectrum and the immense distances separating stars. The physicist Ronald Bracewell explored another aspect of this problem through the concept of interstellar communication networks. Bracewell suggested that advanced civilizations might send automated probes or communication relays across the galaxy. These devices could act as messengers, quietly transmitting information between star systems over long periods of time. If such probes exist, they might operate silently, waiting for the right conditions to communicate with emerging civilizations. But detecting them would be extraordinarily difficult. The distances between stars stretch across trillions upon trillions of kilometers. Even signals traveling at the speed of light require years, decades, or centuries to cross these distances. Communication across such scales becomes a slow and delicate process. Messages sent between stars might resemble conversations conducted across vast stretches of time rather than across moments. This cosmic scale introduces another complication. Civilizations may simply miss each other. One society might develop advanced technology, transmit signals for a few thousand years, and then fade away. Another civilization might arise millions of years later in a distant region of the galaxy. Their signals would never overlap. In a universe billions of years old, the lifetimes of technological societies may be brief flashes in comparison. If those flashes rarely occur at the same time and within the same region of space, the sky could remain quiet even if many civilizations have existed at different moments in cosmic history. The silence might not mean emptiness. It might simply mean separation. Across the vast structure of the cosmos, signals travel. Slowly, distances remain immense, and civilizations may appear and disappear across millions of years. From Earth's perspective, the night sky still seems silent. Yet beneath that silence lies a deeper question about how information travels across the universe, and how astronomers continue searching for signals of all kinds, not only from intelligent life, but from the natural processes of the cosmos itself. Long before telescopes were built to observe radio waves from distant galaxies, the discovery of cosmic radio signals began almost by accident. During the early 1930s, an engineer named Carl Jansky was working for Bell Telephone Laboratories in the United States. His task was not originally related to astronomy at all. Instead, he was investigating sources of interference that affected transatlantic radio communications. To study the problem, Jansky constructed a large rotating antenna designed to detect faint radio signals from across the sky. The unusual device looked somewhat like a carousel made of metal pipes and wires. When he began analysing the signals received by his antenna, Jansky noticed something curious. Among the various sources of interference, one signal appeared to repeat in a steady pattern. It rose and fell in strength once every 23 hours and 56 minutes. That interval matched the rotation of Earth relative to the stars rather than the Sun. The signal, it seemed, was coming from space. After careful investigation, Jansky traced the source of the radio emission to the direction of the constellation Sagittarius, which lies toward the dense central region of the Milky Way galaxy. This observation marked the first detection of radio waves originating from beyond Earth. Without intending to, Jansky had opened an entirely new window onto the universe. His discovery revealed that the sky was not silent in the radio portion of the electromagnetic spectrum. Invisible signals were constantly arriving from distant cosmic sources, carrying information about energetic processes occurring far beyond the solar system. Although Jansky's work was groundbreaking, radio astronomy did not immediately become a major field of research. Much of the early development came from the determination of a single enthusiast. Grote Reber, an American amateur radio operator, was fascinated by Jansky's discovery. Determined to explore these mysterious signals further, Reber decided to build his own radio telescope. In the late 1930s, he constructed a large parabolic dish in his backyard in Wheaton, Illinois. The telescope measured roughly 30 feet across and was designed to collect radio waves from the sky and focus them onto a receiver at its center. Night after night, Reber pointed his telescope toward different regions of the heavens, carefully recording the radio signals he detected. Through years of patient observation, he created the first detailed radio maps of the Milky Way. Reber's work demonstrated that radio emissions were widespread across the galaxy. Regions filled with gas, dust, and energetic particles produced radio signals even where visible light was faint or absent. His dedication helped transform radio astronomy from a curious observation into a serious scientific discipline. As technology advanced in the decades that followed, radio telescopes grew larger and more sensitive. Astronomers began discovering new and unexpected phenomena hidden within radio signals from space. One of the most remarkable discoveries occurred in the late 1960s. At the University of Cambridge, a graduate student named Jocelyn Bell Burnell was analysing data from a radio telescope designed to study distant radio sources. While examining the recordings, she noticed a strange pattern of repeating pulses. The signals arrived with extraordinary regularity. At first, the pattern seemed almost artificial. Some researchers jokingly referred to the source as little green men, imagining that the pulses might come from an extraterrestrial transmitter. But further investigation revealed a natural explanation. The signals were coming from an object now known as a pulsar. Pulsars are rapidly rotating neutron stars formed in the aftermath of supernova explosions. These dense stellar remnants possess extremely strong magnetic fields that channel beams of electromagnetic radiation outward from their magnetic poles. As the neutron star spins, those beams sweep through space like the rotating light of a lighthouse. If one of those beams crosses Earth, astronomers detect a brief pulse of radio waves each time the star rotates. Some pulses spin several times per second. Others rotate more slowly, but all exhibit remarkable precision, with pulse intervals so regular that they rival the accuracy of atomic clocks. The discovery of pulsars, credited to Jocelyn Bell Burnell and her research supervisor Anthony Hewish, revealed another layer of cosmic activity hidden within radio signals. Objects invisible to ordinary telescopes were broadcasting rhythmic patterns across the galaxy. As radio astronomy continued to develop, scientists learned that many powerful cosmic phenomena emit strong radio waves. Distant galaxies containing supermassive black holes can produce enormous jets of energetic particles that extend far beyond the galaxy itself. These jets emit intense radio radiation as charged particles spiral through magnetic fields at near light speed. Even regions where new stars are forming can generate radio signals. Clouds of cold hydrogen gas scattered across the galaxy emit faint radio emissions at characteristic wavelengths. By mapping these signals, astronomers can trace the structure and motion of gas within the Milky Way. Radio observations therefore reveal a dynamic universe filled with processes that remain invisible in ordinary light. Detecting these signals requires extremely sensitive instruments. Radio waves arriving from distant galaxies are often unimaginably faint by the time they reach Earth. To capture them, astronomers build large antenna arrays that collect radio energy across wide areas and combine the signals to simulate a much larger telescope. One of the most ambitious projects currently underway is the Square Kilometre Array. The Square Kilometre Array will consist of thousands of radio antennas spread across remote regions of Australia and South Africa. When fully operational, these antennas will work together as a single integrated observatory with a total collecting area approaching 1 square kilometre. This enormous sensitivity will allow astronomers to detect radio signals from extremely distant galaxies and probe some of the earliest structures formed in the universe. The observatory will also help search for faint signals associated with cosmic hydrogen gas, map the large-scale structure of the cosmos, and investigate the environment surrounding supermassive black holes. Through instruments like these, astronomers effectively listen to the universe, not with ears, but with radio receivers. Instead of sound waves travelling through air, radio telescopes capture oscillations of electromagnetic fields arriving from across space. The signals are then converted into data that can be analysed, mapped, and sometimes even translated into audible tones. In this sense, radio astronomy transforms invisible cosmic signals into something that can be interpreted as a kind of listening. The universe may not produce sound in the traditional sense, yet it continuously broadcasts radio signals that reveal its hidden activity. Pulsars pulse, galaxies emit jets, clouds of hydrogen glow faintly in radio frequencies, and distant cosmic structures send whispers of energy across billions of years of space and time. Through radio telescopes, astronomers have learned that the quiet sky is anything but empty. Instead, it is filled with faint messages carried by electromagnetic waves. Among those signals lies one of the most important clues about the earliest moments of cosmic history, a faint glow that fills all of space, a relic from a time when the universe itself was far younger and far more energetic than it is today. Even after exploring exploding stars, distant galaxies, and mysterious radio pulses, there remains another signal filling the entire universe. It is faint, it is ancient, and it is everywhere. This signal is known as the cosmic microwave background radiation, often described as the oldest light that can still be observed in the universe. It does not come from a single star or galaxy. Instead, it fills all of space almost uniformly, arriving from every direction in the sky. For astronomers, it represents something extraordinary, a relic from the earliest visible moment in cosmic history. To understand why this radiation exists, it helps to imagine the universe shortly after the Big Bang. In its earlier stages, the universe was incredibly hot and dense. Matter and radiation were mixed together in a glowing plasma where electrons, protons, and photons constantly interacted with one another. Light could not travel freely. Every photon quickly collided with charged particles scattering in random directions. The universe was therefore opaque, somewhat like the interior of a dense fog. But as the universe expanded, it gradually cooled. Roughly 380,000 years after the Big Bang, the temperature dropped enough for electrons and protons to combine into neutral hydrogen atoms. This process is known as recombination, although it was actually the first time those particles had combined in this way. Once neutral atoms formed, photons were no longer scattered constantly by free electrons. Light could finally travel freely across space. The radiation released at that moment has been travelling through the universe ever since. Over billions of years, the expansion of the universe stretched the wavelengths of that ancient light, gradually shifting it into the microwave portion of the electromagnetic spectrum. What began as intensely energetic radiation has cooled into a faint glow detectable only with sensitive instruments. Yet even in its weakened form, it remains one of the most important signals in cosmology. The existence of this background radiation was first detected in the 1960s by radio astronomers Arno Penzias and Robert Wilson. While working with a large radio antenna in New Jersey, they encountered a persistent source of microwave noise that appeared to come from every direction in the sky. At first, they suspected equipment problems. They carefully inspected their instruments, cleaned the antenna, and even removed pigeons nesting inside the structure. But the signal remained. Eventually they realized that what they were detecting was not interference at all. It was the faint afterglow of the early universe. The discovery provided powerful confirmation for Big Bang cosmology, which had predicted that such relic radiation should exist. Once astronomers recognized the significance of this signal, they began designing experiments to study it in greater detail. Several space missions were launched to map the cosmic microwave background with increasing precision. One of the earliest of these missions was the Cosmic Background Explorer satellite, often called COBE. Launched in the late 1980s, COBE measured the temperature of the background radiation across the sky. The results confirmed that the radiation has an almost perfectly uniform temperature. Across the entire observable universe, the background glow measures only a few degrees above absolute zero. This remarkable uniformity revealed that the early universe was astonishingly smooth on large scales. Yet the most important discovery from the COBE mission involved tiny variations within that smooth background. The satellite detected minute fluctuations in temperature, differences so small they amounted to only a few millionths of a degree. These tiny irregularities were not measurement errors. They were real features of the early universe. The cosmologist George Smoot, who played a leading role in analysing the COBE data, famously described these fluctuations as the seeds of cosmic structure. Those tiny variations represented regions where matter was slightly more concentrated than average. Over billions of years, gravity amplified those small differences. Regions with slightly more matter attracted additional material, gradually forming galaxies, clusters of galaxies, and the large-scale cosmic web observed today. In other words, the immense structures that fill the universe today can be traced back to faint ripples in the ancient background radiation. Later missions expanded upon the discoveries of COBE. The Wilkinson Microwave Anisotropy Probe, known as WMAP, was launched in the early 2000s to produce a more detailed map of the cosmic microwave background. Its observations revealed the structure of those temperature fluctuations with far greater precision. WMAP helped refine estimates of the universe's age, composition, and geometry. By studying the subtle patterns within the background radiation, cosmologists were able to determine that the universe is approximately 13.8 billion years old. The mission also provided strong evidence that ordinary matter makes up only a small fraction of the cosmos, while dark matter and dark energy dominate the universe on large scales. A later mission, the Planck satellite operated by the European Space Agency, extended this work even further. Launched in the early 2010s, Planck measured the cosmic microwave background with extraordinary sensitivity. Its maps revealed intricate patterns of fluctuations across the sky, offering the most detailed snapshot ever obtained of the early universe. These patterns encode information about the conditions that existed shortly after the Big Bang. By analysing them carefully, scientists can reconstruct aspects of the universe's early evolution, including how matter was distributed and how the first structures began to form. In this sense, the cosmic microwave background acts as a kind of photograph, not of stars or galaxies, but of the universe itself when it was still very young. The light detected today began its journey when the cosmos was only a few 100,000 years old, long before the first stars ignited. For billions of years it has travelled through expanding space, carrying with it a record of the early universe. Every direction in the sky reveals the same ancient glow. The universe may appear quiet and empty, yet it still contains this faint echo of its own creation. This signal is extraordinarily subtle, but it tells a profound story. It reveals that even the quietest regions of space carry traces of events that occurred billions of years ago. The universe is filled with information, preserved in the radiation that continues to cross cosmic distances. The silence of the cosmos is therefore not an absence of history. It is a stillness layered over an ancient record. And as the universe continues to evolve, deeper physical processes will shape its future, gradually transforming the energetic cosmos of the past into an ever more spacious and tranquil expanse. The quietness of the universe is not only a matter of distance, it is also a matter of time. Over billions of years, the cosmos has been gradually changing in a direction that physicists describe using a concept known as entropy. This idea emerged during the 19th century as scientists began studying heat, energy, and the behaviour of physical systems. One of the key figures in developing this concept was the Austrian physicist Ludwig Boltzmann. Boltzmann sought to understand why certain physical processes seem to move in only one direction. Heat flows from hotter objects to colder ones. Gas spreads out to fill available space. Energy becomes more evenly distributed over time. These everyday observations led to the formulation of the second law of thermodynamics. In simple terms, the law states that the total entropy of an isolated system tends to increase. Entropy can be understood as a measure of disorder, or more precisely, a measure of how many microscopic arrangements are possible for a given physical state. Systems naturally evolve toward configurations that can be realized in many different ways rather than toward highly ordered arrangements that require very specific conditions. Boltzmann expressed this relationship in a concise statement, connecting entropy to the number of microscopic configurations available to a system. The principle can be summarized as entropy equals Boltzmann's constant multiplied by the natural logarithm of the number of possible microscopic states. Although this equation was originally developed to describe gases and heat engines, its implications reach far beyond steam engines and laboratory experiments. The same thermodynamic principles apply to stars, galaxies, and the universe itself. Cosmic systems also obey the laws of thermodynamics. Stars provide a clear example. A star forms when gravity pulls together a large cloud of gas, primarily hydrogen. As the cloud collapses, gravitational energy converts into heat, raising the temperature at the centre of the forming star. Eventually, the temperature becomes high enough for nuclear fusion to begin. Inside the core of a star, hydrogen nuclei combine to form helium. This fusion process releases enormous amounts of energy, which slowly travels outward through the star and eventually escapes as radiation. The light from stars spreads across space, carrying energy away from the dense hot core into the colder surroundings of the universe. In thermodynamic terms, this process increases entropy. Energy begins in a highly concentrated state inside the stellar core. Over time, it disperses outward as radiation travelling through space in all directions. Stars therefore act as engines that gradually spread energy across the cosmos. But even these engines do not last forever. Stars consume their nuclear fuel slowly over millions or billions of years. As the fuel becomes depleted, the internal balance between gravity and radiation pressure begins to change. Some stars expand into red giants, others collapse into compact remnants such as white dwarfs, neutron stars, or black holes. In each case, the long-term trend is the same. Energy becomes more widely distributed, heat flows outward, entropy increases. On cosmic timescales, this gradual redistribution of energy contributes to the calming of the universe. Early in cosmic history, matter was densely packed, and interactions between particles were frequent. As the universe expanded and cooled, matter spread into galaxies and clusters, while radiation travelled outward across increasingly vast regions of space. The universe became more spacious and more thermodynamically relaxed. The physicist Roger Penrose has explored these ideas in great depth while studying the thermodynamics of the cosmos. Penrose pointed out that the early universe, despite its high temperature and density, actually possessed very low gravitational entropy. Matter was distributed extremely smoothly across space, with very little large-scale structure. From a thermodynamic perspective, this smoothness represented a highly ordered configuration. As the universe evolved, gravity began amplifying small irregularities in the distribution of matter. Regions that were slightly denser attracted more material, eventually forming stars, galaxies, and clusters. These structures increased the overall entropy of the universe by creating complex gravitational systems capable of redistributing energy. Black holes play an especially important role in this process. According to theoretical work by physicists such as Jacob Bekenstein and Stephen Hawking, black holes possess enormous entropy. Their event horizons store vast amounts of information about the matter and energy that have fallen into them. In fact, black holes may represent some of the highest entropy objects in the universe. As stars collapse and galaxies evolve, more matter eventually becomes locked inside black holes. Over extremely long timescales, these objects dominate the thermodynamic landscape of the cosmos. Yet even black holes do not remain forever. Quantum effects near their event horizons allow them to slowly radiate energy through a process known as Hawking radiation. Over unimaginable stretches of time, black holes themselves gradually evaporate. The universe therefore continues moving towards states where energy becomes more evenly spread. Hot regions cool, dense structures dissipate, radiation drifts across ever larger expanses of space. Entropy steadily increases. This trend helps explain why the universe appears calm on large scales, as the energy spreads outward and matter becomes more widely separated. Interactions between systems become less frequent. Violent events such as supernova explosions or neutron star collisions still occur, but they become isolated moments rather than constant disturbances. The cosmic environment grows quieter, not because activity stops entirely, but because energy disperses across such vast volumes of space. The same thermodynamic principles that govern heat, flowing from a warm cup of tea into a cool room, also shape the evolution of galaxies and stars across billions of years. Energy spreads, order gives way to more probable configurations, and the universe gradually approaches states of greater thermodynamic balance. From this perspective, cosmic quietness is not mysterious at all. It is a natural consequence of the laws of physics. The second law of thermodynamics quietly guides the evolution of the universe, encouraging energy to spread outward and systems to move toward equilibrium. In the distant future, This process will continue to shape the fate of the cosmos. Stars will eventually exhaust their fuel, galaxies will grow dimmer, the universe will expand ever further, leaving cosmic structures more widely separated than ever before. What began as an intensely energetic beginning will slowly evolve into a far calmer cosmic landscape. A universe where energy has spread thinly across enormous distances. A universe where quietness becomes the natural state. And as physicists explore the long-term future of the cosmos, they attempt to understand exactly how this slow thermodynamic journey might unfold across unimaginable stretches of time. The quietness of the universe observed today is not merely a temporary feature of the present cosmic era. According to modern astrophysics, it is part of a much larger story unfolding over unimaginably long stretches of time. The cosmos is slowly evolving toward an even calmer future. Stars are currently the primary engines of visible activity in the universe. They shine through nuclear fusion, transforming hydrogen into helium and releasing enormous amounts of energy as radiation. This process illuminates galaxies, powers planetary systems, and produces many of the elements that make planets and life possible. But stars rely on fuel, and that fuel is finite. The gas that forms stars is mainly hydrogen floating in vast interstellar clouds within galaxies. Over billions of years, gravity gathers portions of this gas into dense regions where new stars ignite. Each generation of star formation consumes part of this cosmic reservoir. Gradually, the supply diminishes. Astrophysicists studying the long-term evolution of the universe have examined what will happen when this process continues for far longer than the current age of the cosmos. Two researchers who explored these ideas in depth are Fred Adams and Gregory Laughlin. Their work focuses on what they describe as the far future of cosmic evolution. Adams and Laughlin analysed how star formation, stellar lifetimes, and gravitational interactions shape the destiny of galaxies over immense timescales. Their research suggests that the present era of active star formation represents only a temporary phase in cosmic history. Eventually, galaxies will begin to run out of the raw material needed to create new stars. Large clouds of hydrogen gas will either be consumed by star formation or expelled from galaxies through energetic processes such as supernova explosions and galactic winds. Without sufficient gas, the birth of new stars will slow dramatically. The universe will gradually grow dimmer. This transition is already beginning. Astronomical observations show that the rate of star formation across the universe peaked several billion years ago and has been declining ever since. Galaxies still produce new stars, but the overall pace is slower than it once was. Given enough time, star formation will become extremely rare. The stars that already exist will continue shining for long periods, especially the smallest ones. Red dwarf stars, which contain far less mass than the Sun, burn their nuclear fuel slowly and efficiently. Some of them may remain luminous for trillions of years, yet even these long-lived stars will eventually fade. Once their hydrogen fuel is exhausted, they will cool and dim, becoming dense stellar remnants known as white dwarfs. Over vast periods of time, these remnants will continue cooling until they become extremely cold objects, sometimes called black dwarfs. By that stage, galaxies will contain mostly stellar remnants rather than shining stars. The cosmic landscape will grow darker. Meanwhile, another type of object will become increasingly important in shaping the future universe: black holes. Black holes already exist at the centers of most large galaxies, including the Milky Way. These supermassive black holes contain millions or billions of times the mass of the Sun and exert enormous gravitational influence on their surroundings. In the distant future, as stars fade and galaxies evolve, black holes may become some of the most dominant objects in the universe. Gravitational interactions between stars will occasionally fling objects out of their host galaxies, leaving behind increasingly sparse stellar populations. Many remaining stars and stellar remnants will eventually spiral toward the central black hole through complex gravitational processes. Over time, black holes may accumulate large amounts of matter, yet even this process will not last forever. Black holes themselves slowly lose energy through Hawking radiation, a quantum effect predicted by physicist Stephen Hawking. This radiation causes black holes to evaporate gradually over incredibly long periods of time. The evaporation of stellar mass black holes would require timescales far beyond the current age of the universe. For the largest supermassive black holes, the process may take time spans so enormous that they're almost impossible to imagine. Eventually, however, even these objects will disappear. Another factor shaping the future quietness of the cosmos is the continued expansion of space itself. The discovery that the universe is expanding at an accelerating rate means that galaxies will drift farther apart as time passes. Regions of space that are currently visible may eventually move beyond the observable horizon, carried away by cosmic expansion. Galaxies will become isolated islands in an ever-growing ocean of emptiness. In the far future, observers within a galaxy may no longer be able to see most of the universe beyond their local cluster. Distant galaxies will recede so quickly that their light will never reach them. From such a perspective, the universe would appear much smaller and quieter than it does today. The night sky would contain fewer visible galaxies. Cosmic structures would become increasingly isolated. These predictions paint a picture of a universe that grows progressively calmer over time. The energetic youth of the cosmos, filled with star formation and galaxy collisions, gradually gives way to a quieter era dominated by aging stars and cooling remnants. Eventually, even those remnants fade, leaving behind a universe where activity becomes rare and energy is dispersed across vast volumes of space. This long-term evolution reflects the same thermodynamic principles discussed earlier. Energy spreads, structures evolve, and the universe slowly approaches states where interactions become less frequent. In that distant future, cosmic quietness will not simply be a matter of distance. It will be a fundamental characteristic of the universe itself. Galaxies will drift apart across expanding space, star formation will decline, and the remaining objects will slowly cool and fade into darkness. Yet within this quiet future lies a deeper perspective. The universe is not merely a physical system evolving according to thermodynamic laws, it is also the environment in which conscious observers have arisen, capable of studying its history and contemplating its destiny. The realization that humanity lives during a relatively active era of cosmic history invites reflection. The present universe, with its shining stars and visible galaxies, may represent only a brief luminous chapter within a far longer and quieter cosmic story. And understanding that story naturally leads to deeper questions about humanity's place within such an immense and slowly evolving universe. The universe may appear quiet, but it has never truly been ignored. Across centuries of observation, human curiosity has steadily grown alongside the realization that the cosmos is far larger and more complex than earlier generations imagined. The night sky, once interpreted through myth and philosophy, gradually became an object of precise scientific investigation. Humanity learned not only to look upward, but to measure. This transformation began with simple instruments and careful observation, yet it eventually grew into a global effort involving powerful telescopes, observatories, and research institutions dedicated to exploring the universe. These tools allow astronomers to study a cosmos that seems calm and distant, revealing subtle signals hidden within that quietness. The stillness of space has become a laboratory. Among the many institutions devoted to this work, the European Southern Observatory represents one of the most ambitious collaborations in modern astronomy. Founded during the 20th century, the organization operates several major observatories in the high deserts of northern Chile. The location was chosen carefully. The Atacama Desert offers some of the clearest skies on Earth. The air is dry, the atmosphere is stable, and far from large cities, there is little artificial light to interfere with observations. These conditions allow telescopes to detect extremely faint signals arriving from distant galaxies and stars Within this landscape stand enormous instruments designed to collect tiny traces of light that have travelled across cosmic distances. One of the most famous facilities operated by the European Southern Observatory is the Very Large Telescope, a system of powerful telescopes working together on a mountaintop known as Cerro Paranal. These instruments observe the sky with extraordinary sensitivity, allowing astronomers to study planets orbiting distant stars, measure the motion of galaxies, and examine the environments surrounding supermassive black holes. Even faint whispers of light can reveal enormous discoveries. The quietness of space actually makes such measurements possible. Because there are almost no atmosphere or matter between stars, electromagnetic signals can travel vast distances without being scattered or absorbed. When that light finally reaches a telescope, it carries detailed information about the objects that produced it. Every photon becomes a messenger. The ability to interpret these signals depends not only on technology, but also on the work of scientists who carefully analyze the data collected by these instruments. Over time, their efforts have transformed subtle patterns of light into profound insights about the structure of the universe. One astronomer whose work reshaped modern cosmology was Vera Rubin. Rubin dedicated much of her career to studying the rotation of galaxies. Using spectroscopic measurements collected from observatories in the United States, she examined how stars orbit the centers of spiral galaxies. According to classical expectations based on visible matter alone, stars located farther from the center of a galaxy should move more slowly than those closer in, much as planets farther from the Sun orbit more slowly than inner planets. But Rubin's observations revealed something unexpected. Stars far from the galactic center were moving just as quickly as stars closer to the middle. The outer regions of galaxies were rotating far faster than visible matter alone could explain. This discovery provided powerful evidence for the existence of dark matter, an invisible form of matter that exerts gravitational influence yet does not emit or reflect detectable light. Rubin's careful measurements helped establish dark matter as one of the central components of modern cosmology. Her work demonstrated how extremely subtle observations can transform scientific understanding. In many ways, the calmness of the universe makes such discoveries possible. Because cosmic signals travel across enormous distances without constant interference, astronomers can detect incredibly faint variations in light, radio waves, and other forms of radiation. Tiny shifts in wavelength reveal the motion of galaxies. Faint fluctuations in background radiation reveal the structure of the early universe. Minute variations in brightness reveal planets orbiting distant stars. Each of these discoveries relies on the ability to measure signals that would otherwise be lost in a noisier environment. The quietness of space becomes an advantage. If the universe were filled with constant collisions, dense matter, and chaotic turbulence everywhere, many of the signals astronomers rely on would be impossible to detect. Instead, the immense emptiness between stars and galaxies allows information to travel across cosmic distances with remarkable clarity. The universe may appear silent, but its signals remain intact. Astronomical instruments are therefore designed with extraordinary precision. Telescopes must remain stable while tracking objects that move slowly across the sky. Detectors must be cooled to extremely low temperatures to prevent thermal noise from overwhelming faint cosmic signals. Even the location of observatories is chosen with care. Remote mountaintops, desert plateaus, and space-based observatories far beyond Earth's atmosphere all help reduce interference. In these quiet environments, astronomers can detect signals that have travelled across billions of years. A photon emitted by a distant galaxy may arrive at a telescope after an unimaginably long journey. And when it does, it becomes part of humanity's effort to understand the cosmos. This effort reflects something remarkable about the species that inhabits a small planet orbiting an ordinary star. Despite living in a universe that is vast, quiet, and often indifferent to human concerns, people have developed the ability to observe and interpret signals arriving from across cosmic distances. Instruments built on mountain tops and launched into orbit now collect information about events that occurred billions of years before Earth even existed. Through careful measurement and patient observation, astronomers continue to decode the messages carried by light and radio waves travelling through the silent depths of space. The calmness of the universe, once interpreted as emptiness, becomes an opportunity for discovery. It allows the faintest signals to survive long journeys across the cosmos, and it allows observers on a small world to study the vast universe that surrounds them. From these observations emerges a deeper reflection, a realization that cosmic silence is not merely a physical condition of the universe. It is also a setting in which conscious beings have arisen, capable of asking questions about the nature of reality and their place within it. And those questions lead naturally toward the broader meaning of living in a universe that is both immense and remarkably quiet. When the universe is viewed from the scale of human experience, quietness can feel surprising. Earth is rarely silent. Wind moves through trees, oceans crash against coastlines, and living creatures constantly interact with their surroundings. Even the atmosphere itself hums with motion and energy. Sound and activity are ordinary parts of life on this small planet. Yet the wider universe operates under very different conditions. Space stretches across distances so immense that even powerful cosmic events become widely separated from one another. Galaxies drift through vast volumes of emptiness, and the interactions between stars occur slowly, often unfolding across millions or billions of years. From this perspective, the calmness of the cosmos begins to make sense. Quietness is not a sign that nothing is happening. Instead, it reflects the extraordinary scale on which the universe operates. Gravitational physics plays a central role in shaping this calm structure. Gravity is the force that gathers matter together to form stars, galaxies, and clusters of galaxies. Yet gravity also works gradually and patiently. It does not usually produce sudden or chaotic motion across large distances. Instead, gravitational attraction slowly organizes matter into stable systems. A cloud of gas collapses gently over millions of years to form a star. Galaxies rotate in graceful patterns around their centers. Clusters of galaxies drift together through space under mutual gravitational influence. These motions are powerful, but they unfold slowly. The result is a universe where large-scale order emerges from countless gravitational interactions, occurring over immense spans of time. Instead of constant turbulence, the cosmos settles into patterns that remain stable for billions of years. Galactic disks rotate steadily. Planetary systems orbit predictably. Even galaxy clusters follow paths shaped by gravity across the cosmic web. The apparent stillness of the universe therefore arises not from inactivity, but from stability. Physical laws encourage matter to organize itself into structures that persist over long durations. Once those structures form, they often remain remarkably calm. In this sense, cosmic quietness reflects a kind of balance. Energy continues to move through stars and galaxies, yet the immense scale of space spreads that activity across such large distances that the universe appears tranquil when viewed from afar. Some scientists have reflected on this calmness not only as a physical property of the cosmos, but also as a source of philosophical insight. The physicist Freeman Dyson often wrote about the long-term future of the universe and the role of intelligence within it. Dyson believed that life and consciousness might adapt creatively to the evolving conditions of the cosmos, even as stars fade and galaxies grow quieter. His reflections emphasize the idea that the universe provides both challenges and opportunities for thinking beings. The quietness of space may seem intimidating at first, but it also creates an environment where delicate signals can travel undisturbed across vast distances. In many ways, that stillness makes astronomical discovery possible. If the cosmos were crowded with constant collisions and chaotic noise, the faint signals astronomers rely on would quickly vanish. Instead, The calmness of space allows light to travel for billions of years without losing its message. Each photon that reaches a telescope carries information about the place and time where it originated. A faint signal arriving today might reveal the structure of a galaxy formed billions of years ago. Another might reveal the explosion of a distant star that occurred long before Earth existed. These messages cross the universe quietly, yet they contain extraordinary stories. Cosmic silence therefore invites curiosity. The night sky appears calm, but careful observation reveals hidden layers of activity unfolding across enormous scales. Beneath the stillness lie the births and deaths of stars, the collisions of neutron stars, the growth of galaxies, and the slow expansion of the universe itself. All of it continues, even while the sky appears peaceful. This contrast between apparent stillness and underlying activity has fascinated scientists and philosophers alike. It reminds observers that human senses provide only a limited view of reality. What appears silent may still be filled with signals. What appears empty may still contain structure and energy. The universe quietly invites investigation. Freeman Dyson once suggested that scientific exploration is partly an act of learning how to listen more carefully to nature. Telescopes, detectors, and observatories extend human senses far beyond their natural limits. Through them, astronomers detect faint traces of radiation, gravitational waves, and subtle patterns in the cosmic microwave background. Each discovery reveals another layer of the universe hidden within the calm appearance of the night sky. The stillness of the cosmos, therefore, becomes a source of wonder rather than emptiness. It provides the conditions that allow light to travel, signals to survive, and knowledge to accumulate across generations of observers. In a universe filled with turbulence everywhere, such delicate information might never reach us. Instead, the immense quietness of space allows a small world orbiting an ordinary star to receive messages from across billions of years of cosmic history. Seen in this light, the calmness of the universe becomes something beautiful. It reflects the deep order emerging from fundamental physical laws. Gravity shapes galaxies. Thermodynamics guides the flow of energy. Cosmic expansion stretches space itself. Together, these processes produce a universe that evolves slowly, steadily, and often quietly across unimaginable timescales. Within that vast calm, stars shine, galaxies rotate, and light travels patiently across the depths of space. And on one small planet, observers look upward and begin to understand the story written in that quiet sky. The realization that cosmic silence emerges naturally from the structure of the universe brings the narrative full circle. What once seemed like emptiness becomes a consequence of scale, physics, and time. The universe is not silent because it lacks activity. It is silent because its events are separated by distances so vast that their energies rarely overlap. Quietness, in other words, is the natural voice of a universe that is unimaginably large. And within that stillness lies a story that stretches from the earliest moments after the Big Bang to the distant future of stars, galaxies, and space itself. When people first imagine the universe, it is often pictured as dramatic and energetic. Exploding stars, colliding galaxies, powerful cosmic forces shaping the fate of entire regions of space. All of those things do exist. Yet when the night sky is observed with the naked eye, the overwhelming impression is one of calmness. The stars sit quietly against a dark background. The universe appears almost motionless. Nothing seems to be rushing or colliding on a visible scale. Understanding why the cosmos appears so quiet requires looking carefully at several fundamental features of the universe itself. One of the most important explanations lies in the sheer size of space. The distances between stars, galaxies, and clusters of galaxies are enormous. Even the nearest star beyond the Sun, Proxima Centauri, lies more than 4 light-years away. That means the light reaching Earth from that star began its journey more than 4 years ago. When distances stretch across such scales, interactions become rare. Stars rarely collide with one another. Galaxies may pass through one another only once in many billions of years. Even powerful cosmic explosions occur so far apart that their effects remain isolated. Distance spreads activity across the universe, it dilutes energy, and from a distant perspective the result is quietness. Another crucial factor involves the physics of sound and matter. Sound waves require a medium such as air, water, or solid material to travel. On Earth, sound moves through vibrating molecules that push against one another. But interstellar space contains extremely little matter. In many regions of the galaxy, only a few atoms occupy each cubic centimetre. Without a dense medium, sound waves cannot propagate across cosmic distances. Explosions that would produce deafening noise on Earth occur silently in the vacuum of space. The universe therefore lacks the conditions required for sound to travel. Yet this does not mean that the cosmos is inactive. Instead of sound, the universe communicates through electromagnetic radiation. Light, radio waves, infrared radiation, and other forms of electromagnetic energy move through space without requiring a material medium. The work of James Clerk Maxwell during the 19th century revealed how oscillating electric and magnetic fields can travel through empty space as waves. These waves carry information across the universe. Stars shine by emitting light produced through nuclear fusion. Galaxies emit radio waves from energetic particles moving through magnetic fields. Black holes generate radiation as matter spirals inward through accretion disks. Signals travel constantly through the cosmos. They simply arrive as light rather than sound. Astronomical observatories have become the tools that allow scientists to detect and interpret those signals. Facilities such as the European Southern Observatory, the Atacama Large Millimeter Array, and the Square Kilometre Array are designed to capture extremely faint electromagnetic radiation arriving from distant regions of the universe. Space-based instruments extend this capability even further. The James Webb Space Telescope observes infrared radiation from galaxies formed billions of years ago. Earlier missions such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite mapped the cosmic microwave background radiation left over from the early universe. Each observatory acts like a sensitive receiver tuned to a different part of the electromagnetic spectrum. Through these instruments, astronomers detect signals that would otherwise remain invisible. These signals reveal that the universe is far from empty. Supernova explosions release enormous bursts of energy when massive stars collapse. Neutron stars collide, generating gravitational waves detected by the Laser Interferometer, Gravitational Wave Observatory, through the pioneering work of scientists such as Rainer Weiss and Kip Thorne. Magnetars unleash intense flares of radiation produced by powerful magnetic fields described in theoretical models developed by Robert Duncan and Christopher Thompson. Even the faint glow of the cosmic microwave background radiation carries information about the conditions that existed when the universe was only a few 100,000 years old. These discoveries show that the quiet appearance of the cosmos does not mean that nothing is happening. Instead, activity occurs across enormous distances and timescales. Events that appear dramatic locally become subtle when spread across billions of light years. Cosmic expansion adds another layer to this quietness. The discovery of the expanding universe by Edwin Hubble revealed that galaxies are drifting apart as space itself stretches. Later observations by Saul Perlmutter, Brian Schmidt, and Adam Riss demonstrated that this expansion is accelerating due to the influence of dark energy. As galaxies move farther apart, interactions between them become even less frequent. Clusters of galaxies gradually separate. The universe grows more spacious. And over time, cosmic activity becomes increasingly isolated. Thermodynamics also contributes to this trend. The work of Ludwig Boltzmann established that physical systems tend to evolve towards states of higher entropy, where energy becomes more evenly distributed. Stars convert nuclear fuel into radiation that spreads outward through space. Black holes eventually evaporate through Hawking radiation. Energy disperses across ever larger volumes of the universe. This gradual spreading of energy leads to a calmer cosmic environment. Over immense stretches of time, the universe moves towards states where interactions become rarer and structures become more widely separated. Seen from this perspective, cosmic quietness emerges naturally from several fundamental properties of the universe. Vast distances reduce interactions. Vacuum conditions prevent sound from travelling. Electromagnetic radiation carries signals instead of pressure waves. Cosmic expansion spreads galaxies farther apart. Thermodynamics gradually disperses energy across larger regions of space. Together, these factors create a universe that appears calm, even while extraordinary events unfold within it. What seems silent at first glance becomes rich with hidden activity once the correct instruments and theories are applied. Astronomers have learned to listen carefully to the faint signals arriving from across cosmic distances. Every photon captured by a telescope carries information. Every radio pulse reveals something about the physics of distant stars. Every gravitational wave detection tells the story of massive objects colliding far beyond the Milky Way. The universe may look quiet, but it is constantly communicating. Understanding that quietness requires recognizing that human senses evolved for life on a small planet, not for observing phenomena spread across billions of light years. Once instruments extend those senses, the silent sky becomes filled with signals waiting to be interpreted. The calm appearance of the cosmos therefore becomes a reminder of its scale. A scale so vast that even the most powerful events are separated by distances that soften their presence. And that realization naturally leads toward a final reflection, not only about the physics of cosmic silence, but about what it means for conscious observers to exist within such an immense and quietly unfolding universe. The universe often gives the impression of quietness. On a clear night, the sky appears still. The stars shine steadily, distant and calm, scattered across a dark background that seems almost empty. Nothing appears to move. Nothing appears to change. Yet that stillness is only the surface of a far deeper story. Across the cosmos, stars are constantly being born and dying. Galaxies drift through enormous gravitational structures. Black holes swallow matter while launching jets of energy across intergalactic space. Neutron stars collide with such violence that they ripple the fabric of space-time itself. The universe is not silent because nothing is happening. It appears silent because everything is happening across unimaginable distances. Cosmic scale changes how activity is perceived. When events are separated by millions or billions of light years, their energy spreads across vast volumes of space. Explosions that would be deafening nearby become faint flashes of light by the time their signals reach distant observers. Space itself also plays a role. The vacuum between stars contains almost no matter, preventing sound from travelling in the way it does on Earth. Instead of vibrations moving through air, the universe communicates through electromagnetic radiation. Light carries the story of the cosmos. Every photon arriving at a telescope represents a message from somewhere in the universe. Some of those messages began their journey billions of years ago, travelling patiently across expanding space before finally reaching Earth. Through those faint signals, astronomers have learned to reconstruct the history of the universe. The cosmic microwave background radiation reveals a snapshot of the universe when it was only a few 100,000 years old. Radio telescopes detect pulsars spinning rapidly in distant regions of the Milky Way. Space telescopes observe galaxies that formed when the universe itself was young. Each discovery reminds us that the calm appearance of the night sky hides immense complexity. Even the large-scale structure of the universe contributes to its quiet nature. Gravity gathers matter into galaxies and clusters, while leaving vast regions of space nearly empty. Cosmic expansion slowly carries those structures farther apart over time. The result is a universe where activity exists, but where enormous distances separate one event from another. The quietness of the cosmos therefore emerges naturally from its structure. Physical laws shape the distribution of matter and energy across space. Thermodynamics spreads energy outward, encouraging systems to move toward equilibrium. Gravity organizes matter into stable structures that persist for billions of years. Together, these processes create a universe that evolves slowly and often calmly, and yet that calmness has provided a remarkable opportunity. Because the universe is so spacious and quiet, delicate signals can travel enormous distances without being destroyed. Light from distant galaxies survives journeys lasting billions of years. Subtle fluctuations in background radiation preserve information from the earlier stages of cosmic's history. Without this quietness, much of that information would never reach us. Astronomy therefore becomes an act of listening. Telescopes, detectors, and observatories extend human senses far beyond their natural limits. They capture faint signals from across the universe and translate them into knowledge about the nature of reality. Through careful observation and patient analysis, humanity has learned to interpret the messages carried by light.